Good afternoon everyone. So I am Dr. MANIVANNAN, working as an assistant professor in the Department of Computer Science and Engineering, PSNI College of Engineering Technology, Tindukkal, Tamil Nadu, India. So I am going to be take the session with CPU scheduling and disk scheduling in OS concept. So operating system is one of the core subject in computer science and engineering, and it is a very important paper while studying on operating system concept by the computer science engineers. They must know about the various operating system concepts in the area of process management, file management, secondary storage management. So a lot of services provided by OS. In that, today the session we start with CPU scheduling and disk scheduling. So what are the basic concepts today we are going to be discuss is CPU scheduling. So day-to-day life we are using the multi-programming or multitasking system in all areas. So what is multi-programming? At the same time we have to use several processes at the same time. So CPU should be the multi-core, and each core will handle of the different task at a time. So multi-programming in the sense day-to-day life, now we are doing playing games, and we are listening music, and we are playing videos, and we are working with the word editor, and we are doing lot of tasks at the same time. That is called multi-programming. So uniprocess which is a single task at a time. So before we are going to be discuss about the things, the scheduling, it's a very important operating system concept of CPU. CPU scheduling, CPU schedules the process. At the same time, the CPU utilization should be effectively and maximize the effective utilization of the CPU. That is a core concept of operating system. So before we are going to be discuss about CPU scheduling, the two cycles we must know about that. What is process? The process is a task. The process is the program is an execution. The process is a segment of code at executing in CPU. So normally the user writing a program, the program is saved into the secondary storage. So while you are executing the program, that is process, that the content of that program should be placed from the secondary storage to the memory. While the memory is having the sufficient data of the process, then should be allocated to the CPU. So the execution of that process in CPU, we call it a CPU burst, CPU cycle. So if you are going to be manipulate or compute, C is equal to A plus B. So A is 10, B is 10. So C is equal to 20. So the 20 is a value for the variable A should be reside in the memory, as well as 20 is a value for the B should be also reside in the memory. Then only A plus B should be added, and then that C will be holding the value of the result of A plus B. That is called the cycle of CPU. So the manipulation of A and B, and which is added by the arithmetic orders, and it's stored in the C. That is called CPU cycle. The process, its execution in CPU, we call it a CPU cycle. Sometimes that the value should be again stored into the secondary storage, that we call it as IO, input and output. So secondary storage, what does mean? That is a hard disk, or we have to use a lot of secondary storage as area day-to-day life. The pen drive, one external disk, external hard disk. So a lot of secondary storage we are using day-to-day life. In PCs and laptops, normally it is called it as a hard disk. So that is called IO. So that is we have to wait to get the IO and store the value into the secondary storage, that is called IO wait. So two cycle is important of the process execution. One is CPU cycle, another one is IO cycle. CPU cycle, the process executing in the CPU, we have to schedule that, that is CPU cycle. So once the CPU executing their process, the result should be stored in IO. IO is storing busy with another variable or another results, that is called multi-programming. So this process should be wait for the IO releasing their content. Right. So now this is a CPU burst and IO burst. So CPU burst, a lot of accumulator commands are there, various mnemonics are there. So what is that? So we are using of load store, add store, and read from file. So load and store, that means the memory, the secondary storage having the values, so we have to load that value into the secondary storage into the memory. The memory we call it as main memory, which is RAM, random access memory. So once the desired value, it's shifted from, it's transit from the secondary storage to the memory, then only that is the value it's to be performed by the CPU. So once we are transit from the secondary storage to the main memory, then we are adding the values, and that is reading from the file the values for A and be, we call it a CPU bus. So entire these commands, that instruction will be handled by the CPU. So after executing these statements by the CPU, these results would be stored again to the secondary storage. The results are main memory, which is volatile. Once power is off main memory, it's clearing the content. So we should use the particularly the next recycle, so the reused by the data, we have to shift it from the memory to secondary storage again. That is called the wait for IO. We call it as IO burst. So both CPU and IO burst involving to performing the the process execution. So both should be manipulated and will be executed by the CPU and IO. So a lot of programs are multi-programming. At the same time, a lot of programs can be executed, a lot of tasks to be assigned to the CPU. So this is some of the others program is using some other commands in the CPU as well as IO. Right. So what is CPU scheduler now? What is CPU scheduler? Lot of process in the machine. If now day-to-day life we are using multi-programming, multitasking, multi-core CPU. That means one CPU central process will be on the core by core. Each core will be handled of the different tasks. So lot of process, we have to select one process and schedule into the CPU. Then only CPU it's executing the process, executing the program. Then only we are getting the computational value. So selecting the process, that process should be ready to execute. What is ready to execute? The process while we are creating, that is the first phase. Then while after creating, it's assigning all the variables and writing into the tables of the values and updating the tables. A lot of global variables and local variables are there. Everything is ready by the particular program. That program is now ready to execute. So there is a ready queue. The ready queue will be on using of all the process which is now currently it's ready to execute. Selecting that one process from that, and we have to schedule into the CPU. That is called CPU scheduler. The CPU scheduler, which is the one, is selecting the ready process from the ready queue and scheduling into the CPU. What are the scheduling criteria? We'll deal by the next slide. Right. So now, what are the design? What are the decisions it's made by CPU scheduling decision? What are the decisions made by the CPU scheduler? The first one, it's lot of processes running or executing in the CPU. So select one of the process of running to waiting state. That means switch, we call it as context switch. So context switch in the sense, one process which has a lot of variables, which has a lot of information, which has a lot of data. It may be a local or it may be a global, right? So now one process is executing in the CPU. Now the another process is ready with higher priority. So what about the currently executing process? The currently executing process now switches from running to waiting state. Which is the lowest priority process now currently executing? One process coming with the highest priority. That means there may be a system process. Now CPU will be on switches from the running to waiting state. That is the first decision. It may be taken by the CPU scheduler. The second one, switches from running to ready state. So one process now executed, the currently executing that. Other process coming with the highest, shortest time, or it is coming first. Then we go for the running process into the ready queue. It will be placed. It's not going to be the waiting state. It's going to be a ready state. The third one, it's waiting to ready. That is switches from waiting to ready. So one process now waiting. The process queue is now free, buffer is free. That waiting process now it's getting all the variables which holds by the some other process, is producing the sufficient input for the process that is in waiting to ready state. The fourth one is terminates, right? It's going to be executing the process in CPU successfully. That is called terminate. Here the decision 1 and 4 we call it as non-preemptive. Once the process is going to be terminated, it is a terminated space. We cannot preempting that process. And the first one, that is switches from running to waiting state, it's also not to be preempted. That is non-preemptive. So two things, all others are we call it as preemptive. So scheduling, it's a process in CPU will come under two things. One is non-preemptive and preemptive. So from the ready queue, CPU scheduler selecting one process and scheduling in CPU. While process executing in CPU, what may happen? It may happen on two things. One is non-preemptive process, another one is preemptive process. So what is non-preemptive? Once the process gets the CPU, It's never to be exited from that CPU until it completes the execution. So once get the CPU, the process completes its task and then terminates. It's never to be preempted, it's never to be go by another state. It may be a waiting state, or it may be ready state, or it may be other states. No state will be allowed. Once the process is getting CPU for the execution, it complete the task completely and then terminated the process. We call it as non-preemptive. So when it's to be happening of the preempted non-preemptive process, if it is waiting for the IO, if the process is waiting to getting the IO to store value or getting the value, then it's to be preempted. That's all. Otherwise, it's never to be preempted. That is called preemptive process. Otherwise, if the parent process now executed, it's complete the task, but the parent process should be waiting for the child process to be terminated. Now, two processes that parent process. The parent process creates the child process. The child process, which is the inherited by the parent process. If the parent process completing their task, but still child process executed, both are non-preemptive. It just means parent process should be waiting for the completion of child process. That is two cases, waiting for IO or it's a terminating of child process. Other than these two cases, non-preemptive process never leaves CPU to execute. Right. The next one is a preemptive. The OS, the operating system. The operating system is a program, is a system program which is act as an interactor between the user and programs. User can write the programs in their own high-level language. The hardware doesn't know about the high-level language, what is written by the user. So we have to have the intermediator, that is OS. The OS acts as an intermediator between the hardware and the user. And hardware and the user. So the interfaces, OS we call it as interfaces, it's between the user as well as the hardware. So it can convert, it can use of anything which is the hardware can understand the language. Normally binary language, machine language is only understand by the hardware. So which type of hardware we are using, according to that OS compatibility is installed. OS will act accordingly to converting from the high level to the machine level language. Not converting, it's the interfaces will be on instructing the hardware. This is the type of program the user can write. So preemptive, the OS is playing vital role of the preemptive process. Once the lower priority process is currently executing in the CPU, at the same time the higher priority process by the system is invoked or initiated, then the lower priority process should be preempted from the CPU, and that highest priority process should be scheduled for the CPU. That is it's monitoring by the OS. Once the process is executing in the CPU, the OS clearly watching what is the priority of that process. If it is having the lowest priority of the executing process, at the same time highest priority process is enter into the ready queue, the CPU scheduler scheduling the highest priority. The currently executing lowest priority process is preempted. That is called preemptive and non-preemptive. Non-preemptive, it never leaves the CPU until the execution completes. Preemptive, it's between the execution of the process, preemptive, and the other highest priority is to be scheduled in CPU. Right. So now the concept of dispatcher. Scheduler, it select one process from the ready queue and scheduling in the CPU, that is we call it a scheduler, that is CPU scheduler. It's monitoring the ready queue, which process are ready to execute, which process has the sufficient data and variables and tables and whatever it may be. Right. When there is a ready queue having the number of process, we have to select one of the process. We have the criteria for that. Dispatcher, it's the selecting process to be gets the CPU. We are selecting the process. Now we have to allocate the CPU, the selected process to be executed. That is called dispatcher. So scheduler and dispatcher are different. It's both are like brothers. So scheduler selecting one process and dispatcher watching that, monitoring that. The scheduler selecting one process, we have to schedule, we have to allocate the CPU to execute. CPU is one of the major resources of the computer. So hardwares and CPU, the resources can be efficiently used by the OS. The OS will be doing all these things. Right. So once the dispatcher is getting to the action, what has happened in that? The first one is a switching context. That is we call it as contact switch. Contact switch in the same. Once the process is created, all the necessary information of the process is stored in process table. So process table, which has the number of process and process ID and what are the variables handled by the process, each and every information about the process stored in the process table, the structure of stack. The stack is one of the linear data structures which is going to be using the storing of this process, right? So that is called context switch. So once the process is currently executed, we are preempting that process, and dispatcher, it's now allocating the CPU for the other process. The exiting process data should be again restored in the process table. Then only we have to again schedule that CPU and allocate the CPU to be executed. We never lose the content of the preemptive process. That is called it as switching context. Then the second one is switching to user mode. So now one system process executing in the CPU, dispatcher allocating system process in CPU. So that is called kernel mode. So two modes of execution by the OS is handling two modes, that is user mode and kernel mode. Kernel mode is highest priority process executing the kernel mode, that is system programs, while using of application programs by the user, that is called user mode. So what we are finishing the system process in the CPU, we have to again switching to the user mode. Then only the user can writing so many programs and they have to execute. That is called switching to user mode. Then the third one is jumping to the proper location. Jumping to the proper location. So some of the process which has a jumping statements like Pascal and BASIC. So a lot of ancient programming languages, they are using jumping statement. So one statement is now executing in the location of 100. The another location which has a sufficient data in 200, so we have to jumping to that. That is called done by the dispatcher. So jumping to the proper location for the selected process, and we have to restart again the process to be scheduling and dispatching of the things. So dispatcher should be fast enough. The dispatcher is act fast and allocate the CPU for the process which are ready. The scheduler selecting one process is given to the dispatcher. Dispatcher having the multiple process, then one process is allocating the CPU. At a time CPU it's executing one process. Even the multi-programming, multi-core, each and every core will dealing at the one task at a time. Right. So here the important term what we are using, that is dispatch latency. What is dispatch latency? Now currently one process is executing. Now other process coming with the highest priority. The dispatcher stopping the process and starting with another process. The time between stopping and starting, we call it as dispatch latency. Latency is a delay, right? So delay between we are stopping one process or process executing successfully and another process dispatching into the CPU, allocating the CPU. That time we call it as dispatch latency. So important term in dispatcher, we call it as dispatch latency. The time between or stopping one process and starting the other process, we call it as dispatch latency. So now the very important questions we have to ask, that is how does scheduler select a process to run? So lot of ready process in the ready queue, how the scheduler is selecting one process to give into the dispatcher. So we have using scheduling algorithms. Lot of scheduling algorithms there, lot of strategy we have to follow. The 5 important criteria in scheduling. What is that? The first one is CPU utilization. So what is the ultimate aim of CPU? The CPU utilization, it's effective. What do you mean by effective? That is maximize the maximize the CPU utilization. We have to maximize the CPU utilization. Always CPU will be busy. The CPU should not be idle. Lot of processes are there. If lot of processes there, CPU always is handling with one of the process for scheduling to execute the process. That is very important. So we should maximize the CPU utilization. That is the first criteria. The second criteria, what is that? That is throughput. What is throughput? So number of process, its execution is completed by the number of process within the time unit or per time unit. So throughput, what is that? If one process coming and executing, within a stipulated time, the process is executed. So that is number of process that complete their execution per time unit. So single time unit is a single clock. CPU will be function with the inbuilt clock. The inbuilt clock is a one wave, it's a sine wave. It will be on a single clock. The single tick, the CPU is going to be executing the multiple process. Now we are using 2.7 or 3.2 or 4.4 gigahertz of the processor frequency, which has a number of processes at a time unit. Per time unit it has to be executed very fast. That is called throughput. The throughput should be also maximized. The throughput and CPU utilization always to be the maximized. This is handled by the OS, by the scheduler. That is called scheduling criteria. Then third one we call it as turnaround time. What is turnaround time? What is the amount of time is executed for the particular process? What is the amount of time? One process created and which is ready, it's placed in ready queue. Once the process coming to the ready queue, that is a scheduling is started. What is turnaround time? Once the process coming to the ready queue and which is get the scheduler selected and which is given to the dispatcher to allocate the CPU and which is non-preemptive or preemptive, or it's going to be executed and completing the particular execution, or it has to be waiting for IO, or to be waiting for storing into the memory, or to be getting the data from the memory. So that's all collectively we call it as turnaround time. The successful execution of the particular process which is from the ready queue to the completing of the CPU execution, we call it as turnaround time. The turnaround time should be minimized. If the process creator as fast, the OS be scheduling the process and releasing all the IO and act fast to storing and loading of the data into the memory to the secondary and secondary storage to the memory, actively OS will be actively working fast and minimize the turnaround time. Then only the effectiveness of your system will be very high. Then the another two final criteria is waiting time and response time. Both should be minimized. The waiting time, the amount of time your process has been waiting in the ready queue. The process ready, now it's coming to the ready queue, but scheduler never selects the process to be scheduling in CPU. That is called waiting time. Right. So it's waiting of lot of time in the ready queue, the system will be hang up. The process is going to be a terminated state. The process lost the data. So lot of hang up, a lot of overhead, lookup overhead by the OS. So it's once the process in the ready queue, it should be on immediately allocated by the scheduler to the dispatcher. So that time we call it as waiting time. And the response time, it's once the request is submitted by the process, and it's between the time between the process submitting the request for IO and which is the first response. The first response, when it is come to get the IO, the time we call it as response time. One process need IO to store the value. That is, request is sent by the process to the OS. I need IO. You just please bring back of the IO to the corresponding process. When the first response by the OS, between this time we call it as response time. This is also should be a minimized one. So 5 important criteria: CPU utilization, and we call it as which should be maximized, and we call it as throughput and turnaround time and waiting time and response time. CPU utilization and throughput should be maximized. Turnaround time and waiting time, response time should be minimized. That's OS will be instructing to the scheduler. You care with these 5 criteria and select one process from the ready queue. So now, based on these criteria, 4 important scheduling algorithm is placed. The first one is a first come first serve. The second one is shortest job first, priority scheduling, round robin scheduling. 4 primary scheduling algorithm in all type of operating system we are using, whether it may be a Windows, or it may be XP or 10, or it may be Linux, or it may be a Ubuntu, right? It may be a Solaris, it may be a iOS. So lot of mobile applications OS, as well as the handheld devices OS. Then based on the scheduling algorithm, it's scheduling the process. Based on this criteria, these 4 scheduling algorithm will be worked out. See one by one. The first one is a first come first serve scheduling. What is first come first serve? Right. So this is a simple example. Number of process here, it's P1, P2, P3, 3 process which has a burst time. The burst time in the sense which is collectively we call it as CPU and IO. 2 kinds of cycle is there, CPU burst and IO burst. That is collectively they call it as burst time, which is the total time to be elapsed the process. That means P1 has 24 milliseconds as a burst time to complete their execution, as well as P2 has only 3 milliseconds to complete the process. P3 also, it has a 3 milliseconds to complete the entire execution of the process. Now this is the order which has come to the ready queue. The order in the sense, the P1 is first coming to the ready queue, then P2, then P3. So first come first serve, which is the process come first, the scheduler schedule that process. That is the algorithm, we call it as first come first serve. So the order, what is that? That is P1, P2, P3 in the order of first come first serve. So here the scheduling algorithm will be represented by the Gantt chart. The Gantt chart is a representation of the waiting time and the execution time and the turnaround time of the particular process. So the Gantt chart, which has a compartment of each and every process, the left side is the waiting time and the right side of the process, which has, we call it as turnaround time. The turnaround time is first, the response time is it's initiated and completing all the burst time. It's waiting for IO and which is coming to the ready queue, and it's completing the execution of the entire process. So now the calculation of the waiting time of this Gantt chart, how it should be, the P1 is a waiting time is 0, because P1 is the first process coming to the ready queue. It's a first come first serve scheduling algorithm. Immediately scheduler it's scheduling P1 to the CPU, so no waiting time for P1. When it's coming to the ready queue, immediately scheduler allocates the P1 into the CPU, so there is no waiting time for P1. So 0 milliseconds is a waiting time for P1. Now P2, its second is coming to the ready queue. So now currently P1 is executed. FCFS is non-preemptive. Once it's allocated the CPU, never to be executed, never to be exited from the CPU until it completes the execution. So P2 is waiting for long time, it's 24 milliseconds. So waiting time of P2 it's 24. Once P1 has completed their execution completely, then only P2 is going to be getting the CPU. So waiting time of P2 is 24. So what about B3? It's very simple. So 24 for P1 and P2 it's 3 milliseconds. So totally 27 milliseconds is the waiting time of P3. So first come first serve, which has come first, that's to be allocated. So what is the average waiting time of 3 process in first come first serve scheduling? The average is P1 is 0 and P2 is 24, P3 is 27. So 51 by 3 is totally 17 milliseconds is for waiting time, average waiting time. So we have 3 process. We have the 3 process which has a 24, 3, 3, and the average waiting time is 17 milliseconds to be waited to complete these 3 processes. So now consider the order is changed now. The order is now changed in the order of P2, P3, P1. So what is P2? It's 3. P3 is 3, P1 is 24. The order is changed now, P2, P3, P1. The burst time of the P2 is 3. P3 of burst time of P3 is 3 and burst time of P1 is 24. Now the order change, first come first serve. P2 is coming first, so no waiting time is 0. Its burst time is 3, and again P3 is comes, which has also 3 milliseconds as a burst time. So it's waiting for 3 milliseconds and executed totally 6. P1 is waiting for 6 milliseconds and 24 up to 24, that is 30. It's a completes of P1. So what is the waiting time? It's a P1 is 6, P2 is 0, P3 is 3. So 6, 0, 3, it's a waiting time of P1, P2, P3. So what is the average waiting time? 6 plus 0 plus 3, 9 by 3 is a 3 milliseconds. So comparing to the first scenario, if it is a longer process first coming to the ready queue, the average waiting time is so high. If the shortest process coming first, the average time is reducing to 3. So much better than the previous case. So that is we call it as convoy effect. So convoy effect, it's a convoy goes there, it's to be on slowly move. Once the VIP gets reached, then only all other public services and all other public transport will be allowed to be getting to the road. So we have to waiting the convoy is to be completed. That is the same. The shortest process should be waited until the longest process is finishing their execution. That is convoy effect. So first come first serve is ineffective once the largest burst time process first coming to the ready queue, the first come first serve, it's inefficiently working. So they go for the another scheduling, we call it as shortest job first scheduling. Simply we call it as SJF. Shortest job first, the scheduler will consider the burst time of the process which has the shortest burst time. That should be scheduled first. So this is 2 kinds of FCFS is non-preemptive. SJF sorry, SJF can be used in non-preemptive as well as preemptive. So both non-preemptive and preemptive SJF to be using that, right? So that is the 2 schemes of shortest job first, non-preemptive and preemptive. So non-preemptive, as I already told, there is no exiting of the process once it get the CPU. Preemptive, at any time the lower priority process can be preempted from the CPU and the highest priority process can be get into the CPU, right? So SJF, which is considered of the next CPU burst, which is very less, that process going to be getting the schedule, right? So this is an example of non-preemptive SJF. 4 process P1, P2, P3, P4 which has the arrival time. So what is the arrival time, which is means all the time values are in millisecond unit. So arrival time, which is the time of arrival into the ready queue by the process, that should be also considered. So non-preemptive arrival time is also given, and burst time, total burst time of each and every process, that is P1, P2, P3, P4. Now we are going to be draw the Gantt chart. So now we have to consider SJF. The CPU burst will be very minimal. That should be considered for first to be getting the CPU. Now P3 has the minimal shortest job, that is 1 millisecond, but what is the arrival time of P3 is 4 milliseconds. At the 4th millisecond only, P3 is coming to the ready queue. So 0, 1, 2, 3, 3 millisecond, no other process is going to be getting to the CPU. CPU will be idle. OS never to be using of CPU to be idle. It should be a maximize of CPU utilization. That's why at the time of 0, only one process in the ready queue which has a burst time of 7, that is P1. So non-preemptive SJF, immediately P1 is allocated to the CPU. While executing the P1, that is second millisecond, at the time of 2 millisecond, the P2 process comes, which is non-preemptive, so never to be exited. P1 complete their entire execution. So total 7 bursts of P1 is executed. At the second millisecond, even though its P2s come with the smallest job, that is smallest burst, never to be preempted by the OS. So P1 is completing their entire execution until that is complete their execution at 7th millisecond. So now P1 is complete. 3 processes there, P2, P3, P4. At the time of 2nd millisecond, 4th millisecond, 5th millisecond, all the process now in ready queue. Now CPU scheduler goes and which has the minimum shortest burst time, that should be scheduled. So now 4, 1, 4, P2, P3, P4. The P3 has the shortest job, that is a minimal burst time. So P3 is now scheduled in the CPU. P3, it's which has the burst time of 1. So again it's P2 and P4, both are the same burst time, but the arrival time, its P2 is earlier, because we have to reduce the waiting time. This is one of the criteria. So waiting time should be reduced. So 2nd millisecond, P2 is coming to the schedule, so P2 is allocated, and 8 to 4, 12 will be the burst time of P2. So last one is a P4. P4 is now scheduling the CPU. So this is shortest job, first non-preemptive execution. Once the process scheduled in the CPU, never to be exited from the CPU. So now what is the average waiting time of this non-preemptive SJF for this example? The P1 is 0, P3 which has a 7, but P3 comes to the 4th millisecond and it gets the 7th millisecond by the CPU. So 7 minus 4 which has the 3 of P3. So P3 is a waiting time is 3 millisecond, which has the 7th millisecond for the CPU, but it comes for the 4th millisecond. So it's a 4th millisecond is entered into the ready queue. At 7th millisecond it gets CPU. So only the difference between 7 minus 4, we call it as 3. So P3 which has a 3 milliseconds to be waited. So what is P2? It gets the CPU in 8th millisecond, but it comes to the ready queue at 2nd millisecond. So 8 minus 2, 6. So 6 will be the waiting time of P2. What is the waiting time of P4 now? The P4, it's getting CPU at 12th millisecond, but the arrival time of P4 is 5. So 12 minus 5 is 7. So 7 will be the waiting time of P4. So once in SJF, once the arrival time is given in the chart, in the example, we must consider the arrival time for calculating the waiting time. So what is the average waiting time? 0 plus 6 plus 3 plus 7 by 4, we get 4, that is 9 plus 7, 16 by 4, it's a 4 average millisecond. So comparing to FCFS, which has of 3 process, but the average waiting time is 17, but here SJF, which has a 4, the average waiting time is 4 millisecond. So SJF is an optimal one for all kind of application, that is non-preemptive. Now we go for preemptive. So preemptive, one, the process, it's getting the CPU, at any time it can be preempted by the CPU. That is preemptive SJF. Now the same example, P1, P2, P3 with the same arrival time and same burst time. So now look at that, the Gantt chart, it's changed, and the average waiting time is also reduced by 1 millisecond. The previous non-preemptive for the same example is 4 millisecond. For the preemptive is 3 millisecond. We are reducing the waiting time. That is one of the criteria of scheduling. So how it is? So the same, at the 0th millisecond, only one process in the ready queue. Immediately CPU scheduling the P1. So P1 is now getting the CPU, it's execute 0th millisecond, 1 and 2. At the 2nd millisecond, P2 comes to the ready queue, which has a 4th burst time. But already P1 is executed 2 millisecond, remaining time of the burst of P1 is 5. But now the second millisecond P2 comes 4, 5 and 4 is compared by the CPU, that is 4 is smallest, so P2 is now getting the CPU, which this call it as shortest remaining time first algorithm, that is SRTF, shortest remaining time first algorithm. Once it's getting the CPU, if the other process come with the least CPU burst, the CPU scheduling that process, we call it as shortest remaining time first algorithm. So second millisecond 4 will become scheduling P2. At the fourth millisecond again P3 commits one burst, the remaining of P1 is 5, the remaining of P2 is 2, but 1 is smaller, so P3 is now scheduling in the CPU. So now P3 has one CPU burst, so 4 to 5 P3 is now getting that. So at the fifth millisecond 4 is come, what is the remaining time of P1, P2 and P4? Now P3 is completed their execution entire burst. Remaining is P1, P2, P4, P1 remaining is 5, P2 remaining is 2, P4 is now come with 4 bursts. So which is the smallest? It's obviously that is P2. So P2 has the remaining time 2, so P2 is now scheduling that. So 5 to 7, its entire execution of the CPU burst of P2 is now complete. Now remaining P1 and P4, P1 has the remaining time of 5 milliseconds, P4 has a 4, 4 is the smallest, so now P4 it's scheduling for CPU. So 7 to 11 which has 4 milliseconds, so it completes. Again it's only P1 which has a 5 millisecond. Now lastly finally P1 it's now getting into the CPU. So this is called preemptive. P1 is preempted, P2 is preempted. P1 it's a second millisecond is preempted and scheduling to the other process which has the less burst. So that is called shortest preemptive SRTF algorithm, shortest remaining time first algorithm. So SJF preemptive is an efficient algorithm for all kind of machines which has a heavy load is there in the machine. SJF should be used for scheduling by the CPU. So which has the average waiting time? How to calculate? So P1 it's a waiting time. What is the waiting time of P1? It's 0th millisecond is coming to the ready queue. So 0 again the Gantt chart has the P1 here 11, so 11 0, but P1 is releases the CPU at second millisecond, again it gets 11th millisecond, so 11 minus 2 it's 9. Right. So P1 it releases the CPU at second millisecond and P1 again gets the CPU at the 11th millisecond. So the waiting time is between this and this. So 11 minus 2 is 9 because arrival time is 0. So 9 is the waiting time of P1. So what is the waiting time of P2 now? The P2 it gets 2. P2 is gets 2 here, it's a second millisecond its arrival, so this 0, but it's a preemptive process. Again we go for P2 here 5, P2 releases the CPU at 4th millisecond, again it gets the CPU in the 5th millisecond, so 5 minus 4 is 1, so 1 is a waiting time of P2. Here there is no waiting time because P2 is coming to the second millisecond in the ready queue, immediately it allocates to the CPU. So no waiting by P2 at the initial allocation. The second allocation it gets 5th millisecond but releases 4th millisecond, so 5 minus 4 it's 1. So what about the P3? It comes to 4th millisecond in the ready queue, immediately it gets the CPU. So 4th millisecond comes to the ready queue, immediately CPU scheduling the P3, so 4 minus 4 it's 0. P3 never waited, so it's immediately gets and the entire burst is executed, so 0. What about P4? It's a 5th millisecond it comes, 7th millisecond is allocated, 7 minus 4 it's 2. So totally average waiting time is 9 plus 1 10 plus 0 plus 2 12 by 4 3. So comparing the same example of non-preemptive, it's a 4 milliseconds of average waiting time, but the preemptive SJF we have 3 milliseconds. So once you go by SJF preemptive, that is otherwise we call it a shortest remaining time first algorithm, which is optimal, effective for any kind of application. So third one, it's a priority. So all of the scheduling it's go for depends upon the application. So how to scheduling based on the criteria we have to use for the priority and round robin. So what is priority scheduling? The priority it's the table which is the example is coming with the integer value, lowest number which has the highest priority. If it's a process coming with the priority of 1 which is the highest priority value. So priority means which is the classification between the user process and system process. System process obviously we call it as the highest priority process. Once the highest priority process enter into the ready queue, immediately the CPU scheduling the highest priority process. So that is we call it as priority scheduling. So priority number associated with each process, smallest number which has the highest priority. If the process has the 4, which is the lowest priority. If the process has 1, which is the highest priority. So that is a example is given to that. That is we have to given that. So both the preemptive and non-preemptive can be used in priority algorithm. FCFS and round robin. If FCFS, we call it as non-preemptive, and round robin, which involves a preemptive or non-preemptive. SJF is also preemptive or non-preemptive. Round robin, it's a preemptive, right? It's a preemptive, right? So what is the problem in priority scheduling? That is starvation. What is starvation? The lowest priority process should wait for a long time for the highest priority process should be completed their execution. If the highest number of priority processes are high in the table, in the ready queue, lowest priority process never to be get the CPU to execute it. That is called starvation. So lowest priority process, it should be always waiting there to get the CPU. Lot of highest priority process coming to the ready queue in between the execution. That is called starvation. So what is the solution is given to that? That is called aging. Aging in the sense, once the lowest priority process coming to the ready queue for the longer time. So at the in between of the execution, the priority of the process should be increased. That is called aging. If it is a 4 of priority, lowest priority. If 1, the number is the highest priority. So 1, 2, 3, it's now executed. Now 4 again is going to be getting the CPU. At the time, the other process with the highest priority coming to the ready queue, immediately that process to be getting to the CPU. So 4th priority process never to be getting that CPU. That is called starvation. So how to resolve this? If it is waiting for a long time by the lowest priority in the ready queue, the OS goes to the ready queue and increasing the priority of the longest waiting priority process, lowest priority process. That is a solution, we call it as aging. As time progresses, increasing the priority of the process by the OS, we call it as priority scheduling. The last one, we call it as round robin. The round robin, each process will get of some quantum of time to get into the CPU. There is no priority, there is no lowest burst, there is no largest burst. Each and everyone in the ready queue will get some amount of time to get the CPU for the execution. We call it as round robin. So this is an example of round robin. So P1, P2, P3, which is the same example we have discussed in first come first serve, 24, 3, 3. Never mind about the burst time. OS is setting the quantum of time is 4 milliseconds. That means each and every process will have 4 milliseconds in the CPU. There is no priority, there is no burst time. So what is the Gantt chart? The order is coming the same order. P1 is now getting 4 milliseconds. That is 24, remaining time is 20. P2 is 4 millisecond of quantum, but P2 has 3 milliseconds as a burst time. Immediately P2 is allocated, is completed there. Then P3 is 3, total quantum is 4, which is minimal. So 10 will be P3, is going to be executed. So again, it's a remaining 20. P2 and P3 is completed their entire execution. P1 is only the remaining process, which has 20. It's divided into 4 milliseconds. So P1, 4, 1, 2, 3, 4, 5. So 5 into 4, 20. The first P1 is 24. So P1 is computed. So round robin, each and every process gets some quantum of time in the CPU and executed. That's why we call it as this round robin. It's a preemptive. It's a preemptive because the 4 milliseconds given to the process. If it is minimal, it's okay. If it is highest, that should be segregated the quantum of time in the CPU. It's going to be using that. FCFS only preemptive process. That is only preemptive process. Priority and SJF, which is both scheduling, that is preemptive scheduling and non-preemptive scheduling. So this is comparing to all the algorithms. This 4 primary algorithm. SJF, we call it as the efficient one of algorithms. We have to using that. Right. So now this is all about CPU scheduling. Now we come to the part of disk scheduling. Very simple. It's about secondary storage scheduling. The secondary storage, we call it as disk. Normally it's a hard disk. The hard disk is a secondary storage we are using to it. Primary storage is a main memory. Right. So primary storage is a main memory. So that's we have to using that. So secondary storage, now we have to scheduling that. So how to scheduling that? So we have to finding some value in the secondary storage. That is, we call it as seeking time. So access time, The access time coming to the two major components, that is seeking time and rotational latency. What is seek time? There is a cylinder, there is a sector. The hard disk which has the hardware configuration of cylinders and sectors. The sectors, it's a decide sectors has the value. The cylinders, number of cylinders is there, we have to rotate the cylinder to go to the corresponding sector. Then only the head will be reading or writing the value from the sectors. So head will be seeking for the particular cylinder of the decide sector, we call it as seek time. What is the rotational latency? Again, the additional time is needed for that to be go for the particular sector to get the value. Then only the head will be on reading or writing the value of the particular sector. So what is a fast access time, which consists of seeking time? We have to find the value data in the particular sector and the particular cylinder. So that is a rotation to be on the cylinder of the decide sector. Some additionally, the sectors is number of sectors. One sector is having the corresponding data. The additional time is needed to go for the corresponding reading and writing of header for the sector, that is called it as rotational latency. So we have to minimize the seek time, that is very important. Minimize the seek time as fast as possible. We have to rotating the cylinder and going to the corresponding sector to read the value by the head. So this is, we call it as disk scheduling. So how to disk scheduling? So disk scheduling, we have the several algorithm of that. We have to see some two algorithms for the disk scheduling. This is also having first come first serve. So this is we call it as the sector values, which has the value. So 98, 183, 37, 122, 14, 124, 65, 67. That's all the sectors which has the values. So the head pointer start with 53 sector, that is 53rd sector, the head is starting point. So the request queue is from 0 to 199. All the sectors are commanded 0 to 199. There is no exceeding value of 199, there is no less value of 0. Head pointer start with 53, and which is going to be getting the rotational of the seeking value of in the particular sector. That is several algorithms to be using that. So this example we come under FCFS. So FCFS is a first come first serve. What is the queue order? In the queue, in the ready queue, what is the sector is comes, that is we have to travel along with that. The disk, the hard disk is rotating from the cylinder to the sector, which is the ready queue having the value in the order. So head starts at 53. So 53rd sector, the disk is start. It's rotating to, again it's 98. That is the first one. So from 53, the head, it's a cylinder is rotating to 98. Again it goes to 183, and again it goes to reverse back to 37. And 122, 14, 124, 65, 67. So what order the sector has in the value in the queue? The head started with 53. The head movement, it's going according to the order of queue is having. First come first serve scheduling. First start with 53 and it moves the sector by the head. That is 98, 183, 37, 122, 14, 124, 65, 67. So what is the problem? It's the highest seeking time. Here the head is now in 183. It's again returned back to the another end which has a 37. So this is the longest seek time of from 183 to 37. So we have to reduce the seek time. Disk bandwidth should be very high. So disk bandwidth should be very high. We have to find the value in the sector in very high manner. Reducing the seeking time, FCFS will easily follow starting from the header to the order is given in the queue, but longest seek time is to be using here. So here 640 cylinders movement in FCFS for this queue order. Longest movement of cylinder. Cylinder movement should be reduced. Then only easily getting the data and place into the memory, CPU will be getting the data. So this is shortest seek time first, that is SSTF, shortest seek time first, that is minimum seek time, we have to using that, avoiding of starvation. This is efficient, like CPU scheduling, here also SSTF is optimal, efficient. So head start with 53, same queue, but it calculates, the algorithm is calculates of shortest seek time. It starts with 53, all this cylinder sector's value, which is the shortest seek time from 53. If it is take 98, which is high, 183, which is high, 37, it's from of 37 to 53 is 16 movement, right? 16 movement, and 122 is which is very high, 14 is high, 124 is high, or 65 from 53 to 65 is only 12 movement. Comparing to 37 is 16, It's 65, it's 12. So from 53 it goes to 65. From 65 so minimum seek time is 67. From 67 is a minimum seek time is 37. From 37 is 14. From 14 is 98, 122, 124 and 183. So SSTF, its algorithm, it calculates from the head. Currently where is the head in the sector? From there which is the minimum seek time. So which is obviously it's an efficient algorithm, we have to using that. So this is SSTF algorithm. So this scheduling which has the FCFS and SSTF, the SSTF is optimal one. From the cylinder movement will be reduced here is only it's a 240. So 240 is comparing to FCF is 640 cylinder movement, in SSTF is only 240 cylinder movement. So minimizing the seek time, once you are minimizing the seek time, disk bandwidth is very high, disk bandwidth is very high, it's high frequency of data transit from secondary to primary storage. That's what the CPU efficiency, the system efficiency, that's algorithm all handled by operating system. So I conclude from here that is today's session we discuss about CPU scheduling and disk scheduling. CPU scheduling, which is very vital primary functionality of OS, and disk scheduling is also monitored by OS. We go for FCFS and SSTF of disk scheduling. So thank you very much for giving the opportunity to take OS concepts for the students who are beneficiary of the operating system concepts as well as computer science engineering. Thank you very much.